Hi, I'm Shanawaz. In this lecture, we will discuss regular functions. Now, analogous to differentiable functions in differential geometry, here in algebraic geometry, we have the notion of regular functions. Now, these regular functions, they are just quotients of polynomial functions. Now, before defining these regular functions, here is a small reminder. So, so one should recall that if we have an integral domain, so if A is an integral domain and suppose S is the set of non-zero elements in A, then the localizer ring S inverse A, which contain elements of the form say A by S, where A is in A and S is in S. So this ring is a field. So this is a field under the operations, under the addition and multiplication, under the addition and multiplication given as, so if we take two elements in this ring, say A by S and B by T, then their sum is equal to AT plus BS over ST, and the product of these two elements is given by, so it is AB by ST, where these A and B, they are the elements of the ring A, and S and T, they are the elements of the set S. So this ring is called the quotient field of ring A. So the field S inverse A is called the quotient ring, quotient field, or the field of fractions, quotient field of A, and is sometimes denoted by Q of A. Here Q stands for quotient. Now let us look at the quotient field of the the coordinate ring of a given affine algebraic set. So we have the following definition. So let X be an affine irreducible algebraic set. So be an irreducible affine algebraic set. So this, so then the quotient field. So then the quotient field uh, Q of A of X. The quotient field of the coordinate ring of X. Now, one can note over here, since x is given to be irreducible, so this ax is an integral domain, because this ax is actually given by the quotient ring of, I mean the quotient of the polynomial ring and the ideal of x. Now, x being irreducible, ix is a prime ideal. So this ring, this coordinate ring, is an integral domain. Now it makes, I mean, then the quotient ring of this ring is a field. We call this ring to be the field of rational functions on x. So then the quotient field q of ax of the coordinate ring of x is called uh, the field of rational functions. Field of rational functions on x, and is denoted by k of x. So this k of x is same as, so this k of x is actually the quotient field of the coordinate ring. So an element of kx is called a rational function on x. So an element of kx is called a rational function on x. So for example, if we look at the, so let us take x to be equal to the affine n space, then the quotient field of x, I mean ax, which is q of a of affine space, which is same as the quotient field of, now the coordinate ring of the affine space is the whole ring, so it is the whole polynomial ring, which is kx1 up to xn. Now the quotient field of the polynomial ring is the field of rational functions, which is given as kx1 up to xn. So here we have these round brackets. Now we use these rational functions to define the regular function. But before this, we first define the local ring at a point. So we have one more definition, which is the definition of a local ring. So suppose we have, so let x subset of a and b an irreducible algebraic set. Let us pick some point p in x. So this is given to be a point. So the local ring of x at p, so this is the set. So we denote this set by this fancy O subscript x comma p. So it is the set of all those rational functions. So it is the set of all those rational functions. So now h being a rational function, so it is the quotient of two polynomials f and g. Uh, so this is an element of kx such that g, I mean g does not vanish at point P. I mean g of P is different from 0. Now this set is called the local ring at P. So one can verify this set is indeed a ring, I mean a subring of Kx. So one can easily see over here, if we have two elements, say H and Q in O of XP. So if H and say Q are in the set O of XP, then H plus Q of P will be by definition of these rational functions. So this will be h of p plus q of p. Now h and q being elements of this set, so this h and q, the denominator does not vanish at point P. So this function, I mean this rational function, is also an element uh, of this set. Similarly, we can show that the product of H and Q is also an element of this set. So it follows that this is a subring of the uh, field of rational functions. So here let us mention this. So we say uh, a rational function over x is defined uh, at is defined at a point, say P in x, if we can write if we can write this h as the quotient of two polynomials f and g, where these elements f and g, they are the elements of the coordinate ring. Now f and g being the elements of coordinate ring, so that means this f represents a class. Similarly, g represents a class because ax is actually the quotient of the polynomial ring modulo the IL of x. So each element in ax is actually a coset, which is an equivalence class. So this is so where f and g are in the coordinate ring of x with g of p different than 0. That is if and only if and this h is in this local ring. So that is if and only if this h is in the local ring of x at point P. Now we can define local ring of an open set. So we have one more definition. So now let us consider an open set. So let U be a subset of X. So this U is an open subset. Be an open subset of an irreducible affine algebraic set. X, then the subring uh, I mean the subring fancy O sub X of U. So this is the intersection of all local rings at point P, where this P is in the set U. This intersection runs over all the pointers in the open set U. So one can see over here this uh, I mean this set also is a subset of the field of the field of rational functions. So this also turns out to be a subring of Kx, and this is called the ring of regular functions on U. So then the subring of O sub x of u of kx is called, so this is called the ring of regular functions on U. So thus a regular function on U is defined at each point of U. So this is defined at each point of U. Now we have some remarks here. So the first remark is, so a regular function on U actually defines a function. So a regular function say h, which is f divided by g on U, defines a function. So it defines a function like h of something from U k, where a point P of U is carried to the point HP of K, which is same as F of P over G of P for uh, some F and G in the coordinate ring X with G of P non-zero. So one can note over here, this is a well-defined function. So I mean this function over here, this is a well-defined function. So note that uh, this is a well-defined function. For if now since h is given to be f divided by g and f and g being elements of ax, since in ax we have the cosets, so a coset depends on the representative, I mean is independent of the representative. So if we choose two different representatives for h, we had to prove, I mean we had to show this function is independent of choice of f and g, I mean independent on of the choice of the representatives. So for if suppose h is given like this, f divided by g, so f represents a class f. Now this class f, this may be equal to class of f prime. So suppose this rational function has I mean one more form, say f prime by g prime. Let us note this by h prime with g prime of p is non-zero. So then now one can note over here that if two elements are equal in the quotient field, if and only if f of g prime is same as f prime g, so then f times G prime is same as F prime times G. Now, if this is the case, uh, so that is F, F dot G prime of P, which is same as uh, Fp dot G prime P is same as F prime P dot G prime P, since the multiplication is pointwise in the quotient field. So now, given that G prime P, this is, this is G of P. Now, given that G prime P and G of P, they are both different from 0, so we can divide through out by G prime P times GP. So this would imply, so since G prime P and G of P are both non-zero, we have, so let us divide this expression throughout by the product of G prime P and GP. So we get F of P divided by G of P is equal to F prime of P divided by G prime of P. So this implies that H of P is same as H prime of P. So hence H of P is same as H prime of P. So that means the function which we define above is a well-defined function. Now we have one more remark here. So suppose H is a rational function on X. So this is a rational function. So then we can write write um, so we can write H as class of F over class of G. I mean the coset of F over coset of G, with F and G being elements of the polynomial ring, and G is a non-zero function. So thus uh, I mean H is in the so let us write this way. So this H is in the uh, ring of local ring of ring of U for the open set U, where U is the complement of the zero set of G. So one can note that this set is closed with respect to Zariski topology. So hence it is, this set is open. So now if H is in this set, so it means that uh, this H does not vanish. G does not vanish. So now this H is given to be the quotient of these two classes. So now if this H is in the regular ring, if and only if this G does not vanish at any point of U. Now this G does not vanish on U because we have taken out the zero set of G. So this means now one can note here this U is the Denison X. So this would imply that every rational function defined as a regular function on an open Dennis subset of X. So thus every rational function defines a regular function on an open dense subset of X. Now we want to identify this set with the set of functions from u to k. So for that we set a notation. We set up a notation. So let u be an open subset of X. So we denote by, say, R of u, the ring of functions from u to k. Now let us take the set of all those functions from u to k. Let us denote those functions by u. So this is a subset of Ru with the property that for each point p in u, there is an open neighborhood. There is an open neighborhood, say w of w contained in u, such that for each p in w, such that for any h in s of u, so this, now h being an element of s of u and s of u being an element, being a subset of Ru, that means this h is a function from u to k. So for this function there exists two polynomials f and g such that, I mean, where g of q is non-zero for all q in w, and this h of q is defined as f of p over g, sorry, f of q over g of q. So then one can see over here this set S of u is clearly a subring of R of u. So indeed S of u is a subring of R of u. Now we claim that this S of u, we can identify this S of u with the ring O of u. So this is our claim. I mean, there is an isomorphism between these two rings. I mean, a ring isomorphism between S of u and O sub x of u. I mean, the ring of regular functions on u. So we have a theorem here. So we claim that the map, say alpha from the ring of regular functions on U to the set S of U, while mm, where this alpha carries an element in this ring which is a rational function to the function h, this, so h square bracket is the function from u to k. So this is our claim. So it is not I mean, it is easy to see that this h is a homomorphism. So all we need to prove is that this h is actually a bijective map. And so let us prove this. So this alpha is an isomorphism. So let us prove this. So first we need to see that the image of alpha is inside S of u. So first we need to show that the image of alpha is inside S of u. So for this, let us take some element in this ring. I mean the ring of regular functions on u. So let h be a regular function over u. So if this is the case, and let us pick some point in u. So this p is some arbitrary point. So then we can write, this h as the class of f over class of g for some elements, for some polynomials f and g in the polynomial ring with g of p different from 0. So one can note that this point p, this is in u minus r of g. So note that um, p is inside the set x minus uh, the zero set of g. I mean, it is inside u but not a zero of g. So one can note that uh, z of g is closed, so this is an open set. So since the zero set of g is closed, the set w, which is equal to the u minus zero set of g, is open. So this is given to be open. So this is open neighborhood of p. So we write NBD as a shorthand for neighborhood. So therefore on W we have, so therefore on W we have, so we can write H of Q as F of Q over G of Q for all Q in W. So this shows that the element alpha of H, which is H with these round brackets. So this is an element of S of U. So this proves or claim that the image of alpha is inside S of U. So now it remains to prove that this alpha is bijective. Now to show alpha is bijective, we exhibit its inverse. So now we exhibit the inverse map beta from SU to the ring of regular functions of U. So we have to exhibit this inverse of alpha. So for that, so let us take some element L in the ring S of U and some arbitrary point P inside U. So let us take W to be an open neighborhood of this point P, and suppose F and G are the polynomials in the polynomial ring kx1 up to xn with L of q equal f of uh, q over g of q. So this follows from the definition of S of u, because if we pick L to be an element of S of u, this L has to follow these this hypothesis. I mean, for L we have I mean, for any point P in U, we have an open neighborhood W of P and polynomials F and G with L of Q is equal to F of Q and or G of Q and G of Q to be non-zero. So this follows from the definition of uh, what do we call S of U. So then we put uh, H to be equal to the class of F over class of G. So we claim that beta beta L is actually H. So we claim that beta of L is actually equal to H. I mean, this beta is the inverse of alpha. Now this follows. This is trivial from definitions. So one should know that it is well defined. That is, I mean, it is well defined because this is independent of the choice of the elements F and G. So this is trivial from the definitions. I mean, from the definitions of S of U and O sub X of U. So if one only proves that H is independent, so for this beta to be a well-defined function, so this H has to be independent of the representatives of these two classes. Here the representative of this class is F and of this class is G. So if we show this H is independent of the representatives, we are done. Now let us show this H is actually independent of the choice of F and G. So let the is an open neighborhood. So let there is an open neighborhood, say W prime, uh, of a point, say P prime, such that L of Q is equal to F prime Q over G prime Q. Now one can note that, so note that if we let W prime to be equal to W intersection W prime, so then this W prime is an open neighborhood, an open set of X. So this is an open set of X because both W and W prime are open. So this is an open subset of X. But X being irreducible, W prime and W double prime is also dense in X. Since X is irreducible, W double prime is a dense subset of X. Now, if we show that, if we show that F of Q or G of Q is same as F prime Q or G prime Q on this W, then we are done because W double prime is a dense subset of X. So if now on W double prime we have, so we have F of Q over G of Q is same as F prime of Q over G prime of Q, because we choose this W prime to be the intersection of W and W prime. So that is F of Q times G prime of Q is equal to F prime of Q times G of Q, or F of Q G prime of Q minus F prime of Q G of Q is 0, and hence F dot G prime minus F prime dot G is a 0 function on W prime. Now W prime being dense in X, so if F dot G prime minus F prime dot G prime is 0 on W prime, so it is 0 on X as well, and hence on X, because F prime G and G prime, they are the elements of the ring, polynomial ring. These are the polynomials, so they are 0 everywhere. This polynomial is 0 everywhere because W prime is dense subset of X. So this would imply, so this implies that uh, the class of F times class of G prime is equal to the class of F prime dot class of G prime, or class of F over class of G is equal to class of F prime over class of G prime. So this shows that this this function beta is well defined. So hence alpha is bijective. So from from hereafter we'll always identify the ring, the ring of regular functions on U with the a ring of functions from U to K. So let us make this a remark. So hereafter we will always identify the ring O sub x of U with the ring of functions from U to K.